Okay, I think we can now start. So before we considered the Euclidean section of the Schwarzschild solution. We started from the Lorentzian space that we analytically continued the time coordinate to Euclidean space, and we imposed the regularity of the Euclidean solution. We obtained what is called the Euclidean section. Section because in principle you can imagine this solution with complexified values of the metric and of the other fields that may be there. Here there was just the metric, but there could be a gauge field or so on. And you slice inside this larger complexified space, you slice the solution in such a way that you have a Riemannian positive definite metric, which is regular everywhere, and it's called the Euclidean section of the, in this case, Schwarzschild solution. And the identification of the time circle, the Euclidean time circle, leads us to conclude that whatever quantum field theory we do in the black hole background, it is a QFT at finite temperature, and the temperature was precisely the working temperature. So the representation for the the path integral, so if we want to compute a partition function for these fields, it will be z of beta, which is trace of e to the minus beta h. So we will be in the canonical ensemble, and the path integral representation will be this one. We have the Euclidean action of our field, say phi, in the background given by the Euclidean section of Schwarzschild. So G, here I mean this matrix that we studied before with the prescribed identification of the coordinates. So this is the canonical ensemble. It describes at state equilibrium between the black hole, and which has some temperature, and the gas that you may have, quantum gas that you may have outside. This is what is called the Hertol-Hawking state, which is an equilibrium state. In what is the canonical ensemble, we have a fixed temperature Th. Since the black hole is evaporating, but the gas outside is at the same temperature, so everything is at equilibrium. Now we go and analyze. I introduced these extra chemical potentials before because these are relevant for a black hole that is rotating and charged. So let's see a bit more sketch in a way how exactly things go by using what we saw before. So we consider now the Kerr-Newman solution. We introduced this some time ago, so now we come back to that. The regularity of the Kerr-Newman solution, and there will be a grand canonical ensemble now. So I'm not going to rewrite the Kerr-Newman metric. You have it in the notes. We have seen it a couple of times. But just recall there was this important polynomial that was quadratic. It had roots. There was R plus and R minus. And the coordinate system was degenerate in R plus and R minus. And now if we go to we can think that now we are in Euclidean space. Again, we start from infinity. We approach what? First we will have plus. We had R plus larger than R minus, larger than 0. So we will find R plus. And by simple argument, as for Schwarzschild, we will conclude that the space ends there. The Euclidean space will cap off there. And that will be our manifold. Something similar to this. Something similar to this one. This will be R equal R plus. But now we have rotation, so there will be some interplay between the two manifolds, because one is, there is rotation, we go to Euclidean space, it's no more rotation, but it's some sort of vibration of one over the other. We are going to see. So what I want to describe is the space between R plus and infinity. So let's, we are sure that symptotically things are fine. We need to go and check what happens close to the horizon, that now is no more an horizon. So we do the change of coordinates, similar to what we did before. I just have some numerical factor that is different, but never mind. So we introduce a new coordinate rho that is defined such that when rho is 0, we are at R plus, and so we move a little bit out of R plus. And now I'm not going to spell out all the details. Also, you will need some mathematical program, some code to do it quickly. Otherwise, it takes some time to do the expansion of all the functions, rearrange things in a convenient way. But the form of the matrix that you get is rather similar to what we have upstairs, just the terms are more complicated. I'm not spelling out what are the functions g theta theta, g rho rho. The reason is they are not important for what we are going to say. They are functions, these are functions of theta and also of r, d phi minus omega dt minus small omega rho squared dt squared. So you can check the matrix will take this form. Hope you can see this. So there is something that is basically what we already had. Now t is still the Lorentzian time, but I can take t equal minus I tau, go to Euclidean. This is something we will do in a second. So once we have done that, this will be the matrix on flat space in polar coordinates, and already we see that there is the surface gravity here, and so we will have identifications that are controlled by the surface gravity, which is very good because it's again the Hawking temperature. Let me remind you what was the surface gravity in this case. It was expressed in terms of these roots R plus and R minus. Just to remind you, these R plus and R minus were functions. It was m plus or minus square root of m squared plus p q squared a squared. Sorry, there was a minus here, a squared plus q squared. Let's set p to 0. I don't want to discuss magnetic charge. I think it was that. So anyway, kappa is r plus minus r minus divided by 2 a squared plus r plus squared. Yes. And so this is as far as this part of the matrix is concerned. Then there is omega here. It's not that I put it comes out from the analysis. Yes.
So if I equivalate the time of this black hole, don't I get from the term that is linear in T?
Sure. Here there is an I. It's a complex matrix. It's a complex matrix, as similar to what we already saw before, when we were not discussing the black holes yet. Okay, this is what you get. Try to do this, you play a bit with mathematics, you see that the matrix has this form. These functions are, again, these g are functions of theta, and then you are expanding in rho, so they will have an expansion in rho. This is you can take the leading order term, but there are other terms. So let me also say it's a function of theta and rho. And in order to fix this kappa, you need to make sure that you also control the terms of order rho squared here, and also the term that is of order rho squared in phi. It's a bit delicate. I spelled a bit more of details, just a few more details in the notes. But this is what you get. And you need to make sure, this term is not something we are going to be interested in, but to fix this, you also need to have control on that. Yeah, it's also, I think it's also a function of theta and not of rho. This omega would be just a function of, It may also have an expansion in rho, but the leading order is finite and is a function of theta, the leading order piece. I didn't write this down here because they are not important. What is important are the leading contributions. Because now we would like to say, let me see if I'm missing something. Yeah, let's see this from two perspectives. One is, okay, we would like to identify the time as we did before. So we would say, okay, identify, first I go Euclidean, so t becomes minus I tau, and then this kappa times tau must be defined up to 2 pi. It must be identified with periodicity 2 pi. So I would something like tau is identified with tau plus 2 pi over kappa, which is the inverse Hawking temperature, which is good, is what we expect. But that's not the end of the story, because this circle we are discussing, this time circle, Euclidean time circle, shrinks at 0 size in rho equals 0. But here we have a component of the matrix, this mixed component d phi dt that comes out of the square, that has a finite term. This is a constant. Omega is this one, is a constant. And this is not well defined in rho equals 0. So it would not be a regular configuration, a regular solution.
Why is it not well defined?
dt, that becomes d tau, is not well defined at the origin of space. We are in polar coordinates. Angular direction in rho equals 0 is not well defined. So we need that whatever term contains dt, it goes to 0 in rho. It's like the metric on the sphere, d theta squared plus sin squared theta d phi squared. You make sure that where d phi is not defined, that is in theta equals 0 or pi, this term goes to 0. It's a regularity condition. Is it convincing? It's the usual regularity conditions that you impose. You may also see that if you complete the inverse matrix, okay, let me not go to that. There are some infinities that in some components that's confusing. But okay, this is the fact that this one form, differential, is not well defined at the pole. If I am at the poles of the sphere, in this case, I have this again. I just have to repeat what I just said. I have the flat space in polar coordinates, and the differential is not defined here. I'm repeating because I see you are not too convinced. But dt is an angular coordinate. We are identifying this. It has become an angular coordinate now in Euclidean. Okay, so this is one point of view. So this means that, what does it mean? That we have to change the phi coordinate. We should not take the identification I just wrote, accompanied by t phi identified with tau phi identified with tau plus beta comma phi, where beta is 2 pi over kappa. We should not do this. We also need to identify phi differently, as we saw before, because this is not a good one form in this space. It's a singular configuration. If we do this, this is not a good identification. I'm coming to the right identification. But let's also observe that, remember, in a Lorentzian signature, we had this vector that becomes null at the horizon, which is dt plus omega d phi. This was the vector that was the null killing vector at the horizon. And okay, we can also continue this to Euclidean signature if we do t that goes into minus I tau Then we have I del tau plus omega del phi. But this maybe we will do later. Anyway, it is still true that the norm of this vector is 0, even after we have done this. It is true that it is 0 at the horizon in r equal r plus. Either way you compute it, you can use these coordinates or these analytically new coordinates. It is xi dot xi is 0 in r equal r plus. So this is teaching us what is the direction that shrinks in the geometry. The direction that shrinks is the one defined by this vector. So it also teaches us what is the time coordinate that must be identified properly. It's the one defined by the action of xi. That is, I should first find coordinates such that xi is del tau hat, t hat or tau hat after. Let me work in Lorentzian signature because it's what we have done before. We had continued the coordinate t hat after having identified it. So this I could also work in this analytic continuation, but let's first find these coordinates. Once we have found this, we know that we have found a direction that shrinks, and it is the one that needs to be identified without issues, because it's the only one that is the direction that shrinks, and that's the only one. And surprise, this is exactly the same things we were doing before. So I need what is t hat? I have to introduce a change of coordinates between t phi and t hat, phi hat. Phi hat does not appear here, but I have to define the generic change of coordinates. So I have to go from t phi to t hat phi hat. Now, again, modulo usual confusing signs should be t hat equal t as before, and phi hat is linearly related to t phi minus omega t. And if I did things properly, seems so, this offending piece goes away. This is just d phi hat. D phi hat. So now that we have aligned our coordinates to the direction that is the, say, problematic one, the one that defines the cigar over there, here it's a bit twisted because of the rotation, because of the presence of this term. Now that we have done that, we've changed our coordinates in such a way that we are better aligned to the situation. Things are very simple. This term is not there anymore, and this t becomes dt hat. Just I put a hat there, is change of coordinate is this, t is t hat, and I can do the identification. So the correct identification is tau hat, phi hat, identified with in this way, where tau hat is, just for clarity, I times t hat. Is there any question about this? We can also go back to the original coordinates. Maybe I'll write it down here so that we have all the changes of coordinates in. So in the original coordinates, the identification should be t phi is identified with t minus I beta phi minus I omega beta. I think already here I have some different relative signs with respect to the previous case. There must be something wrong. If you find it out with some degree of confidence, let me know. I'll also go through it once again. Anyways, it's this should be the right thing. And so as far as rotation is concerned, we are in good shape. We have kind of understood what's happening. Imposing regularity of the geometry. Now the geometry is regular because now I'm identifying phi hat up to 2 pi, and the identification of phi hat is independent of the identification of t hat that is there. So everything is regular now and is not rotating. Again, at the horizon. Again, you could ask, where is omega? Where has omega omega gone. Now I have removed it from this near horizon geometry. Here we are near to the horizon. Omega has disappeared. I don't see it. But we have done this change of coordinates. It will show up at infinity. At infinity, before I had separate dt squared and d phi squared term. Now, by the change of coordinate, I introduce a mixed term. So I move the rotation at infinity. Basically, what's happening, I'm going to write down the matrix in a second, but it's like if we are choosing a system of coordinates that rotates together with the hole, we are in equilibrium with the black hole, because even at infinity we are rotating, and therefore we are ensuring equilibrium with the rotating black hole. So we are in the grand canonical ensemble. We are fixing the velocity omega. But before concluding all this, we already see where we are going, we need to treat the gauge field, right? There is some electric charge, gauge field. Before we saw that the grand canonical ensemble in the path integral representation can be described by introducing a Wilson line for the gauge field that contains the information about the electric potential, the capital phi. And so I would like to see if this is also something that we have to do here, or maybe is not a feature of this space-time. Let's see. So let's look at the gauge field. For the moment, I don't have a regular solution. I have a regular matrix. I need to check that the gauge field is also regular. So A, gauge field of Kerr-Newman. I just copy the part that does not depend on the magnetic charge. So I'm setting the magnetic charge to 0. Minus phi dt hat. And I'm also using the coordinates t hat and phi hat because they are the ones that we are now using to describe the space-time. Then there is a function here that is not so important, but let me just write it to show that it does not depend on rho. It's a function that contains q, the charge, of course. It's not too important for what I'm going to say now. Then there are all terms that are of higher order in rho. Again, here I repeat, there are also terms of higher order in rho hidden in the different components of the matrix. And the phi that you find here is not something I'm introducing by hand. It's what I get from this analysis. Is q r plus over r plus squared plus a squared. So you first need to introduce this t hat coordinate. If I had here, you need to do this expansion in this way. And what you get is precisely the electrostatic potential that I told you is the right one. I don't think I just gave you the definition. It's defined, phi was defined that as A contracted with the vector xi evaluated at the horizon and the outer horizon. In this case, there was no contribution from infinity. Maybe there was a minus depending on the conventions. In principle, there could also be a contribution from infinity that you would subtract. But in these coordinates, the field at infinity is 0. So this was the definition. But now we get it really from the fact that basically here we have dt hat. So it's like contracting with xi. The contraction with xi is del t hat, so just takes this piece of the gauge field, right? This component of the gauge field is what I obtain if I do this contraction. So it's not surprising. But now, okay, we have a gauge field that remains along with the component along t that remains near to the horizon. But we said that this coordinate, this differential dt, this one form, is not well defined in rho equals 0. Is what the argument we used here. Is not well defined. Also, a non-zero component of a dot xi, this one, which is this phi, gives some problems because if you compute the norm of a, you will get infinity because there is a component of the matrix that shrinks, and you're evaluating 1 over that. 1 over g t hat when you compute the norm of this, there would be this. No, it's G mu nu, A nu, so there is the inverse metric, and I'm saying that a component of T hat would give rise to this, and this goes to 0, so I have a term that is blowing up. So this term is singular again. Same argument as before. This differential dt hat is not well defined in rho equals 0. It also leads problem when I evaluate the norm of the gauge field. So it's not a good gauge field. It's not regular. So we can play with gauge transformations. So you could think, okay, gauge transformations are just a redundancy of the description of the system. We don't, I mean, one description or the other is the same. Yes, but here we can do large gauge transformations that change this. And this changes the physics because they affect the gauge field at infinity. So let's do this. Define a gauge field A hat, which is different from the previous one by a gauge transformation. Is A plus phi dt hat. Okay, in this way I remove this bad term here, and the configuration near to the horizon is regular. And is also regular everywhere else outside the horizon, up to infinity. So now we have fixed completely regularity of our solution. Sorry? Yeah, it's a gauge transformed field. This is a constant times dt hat. The field strength doesn't change. So it will certainly still solve whatever field equation you're imposing. Now let's see what some observer at infinity will see. Now we have imposed regularity near the horizon because we want the whole solution to be regular. But we consider from the point of view of the observer at infinity, let's see what the metric and the gauge field are. For the gauge field, it's super simple. We have it there, A hat at infinity. Everything that was here goes to 0 because this field was going, if you check the explicit expression, dies off at infinity. But we have this remaining term now. So at infinity, we have this Wilson line. Now I assume this T hat is becoming T hat is minus I tau hat. This is minus I phi d tau hat. And tau hat is identified as we declared should be identified up to shift in beta. And therefore, I have a Wilson line for the gauge field. Wilson line is just a fancy name to say a constant component along the time direction when the time direction is identified. So to do this, just I repeat, I had to do a large gauge transformation that is a transformation that does not die off at infinity. The parameter lambda would be phi times t hat. Now this is the parameter of the gauge transformation. It's not decaying at infinity. It remains constant, linear in t hat. And the metric, now the metric, ds squared hat in the hat coordinates. So let me say this tends to this field at infinity as r goes to infinity. Same for the metric, goes to dr squared plus r squared d tau hat squared plus d theta squared plus sin squared theta d phi hat minus I omega d tau hat I had an r squared. Sorry, must have done something not good. Yes. So this is locally, it's the metric of Minkowski space. No more Minkowski, really, because we are Euclidean, so flat space, Euclidean flat space, R4 locally, because we can change coordinates here. But we have this imaginary component that causes, apart from the fact that it is imaginary, but it introduces a d tau, d phi term. And again, the coordinate identifications are affected by this. I have to supplement this local form of the metric with the coordinate identifications that are up there. Just I copy it here because they are part of the definition of the background. And the independent coordinate identification, of course, is tau hat, phi hat, that goes in tau hat, phi hat plus 2 pi. This we always have. So with these identifications, the space, full space-time, full space is regular. And we see that we have somehow transferred the rotation omega and the electrostatic potential from the hole to the observer at infinity, in the sense that the observer is now raised at the potential phi and co-rotating at the angular velocity omega of the black hole. So it is in equilibrium. The situation is in equilibrium. And because of this component of the metric here and of this component of the gauge field, due to what we saw this morning, we conclude that we are describing a quantum system in the grand canonical ensemble at equilibrium with the hole. And to specify the grand canonical ensemble, I have to give what the angular velocity is, what the electrostatic potential is, and what the time period beta is. And here we have given all of them. All of them are written, well, omega, phi, they are the expressions that I wrote before. Beta, omega, and phi, they are those of Kerr-Newman, those of the Kerr-Newman solution. Yes? No, but here I'm at infinity. The tau coordinate is not shrinking at infinity. You see, there is no, I'm not forming, the geometry at infinity is not the same geometry as near the horizon. The geometry at infinity is really the one of, let's look what the geometry is. So there is, well, I should do this at fixed r. I take a hypersurface at fixed r, let's say r0. So I fix r0 very large so that this metric is correct, but fixed. So what remains is this time circle, and then I have the metric of a two-sphere that is fibered over a time circle. So fixed r, the geometry is a time circle, tau hat, and then over it I have a two-sphere fibered over it, and this determines the vibration. And it's regular. Okay, so is there any question about this interpretation? So conclusion, both for Schwarzschild and for Kerr-Newman, we have done this Euclidean analysis, impose regularity. Imagine we have a quantum field for which we want to compute the path integral. We first impose regularity of the background. As it was asked before, it's regularity of the classical solution. Now I'm going to motivate why this is also important in the path integral. Then we want to quantize and compute the path integral for a quantum field, and we impose the periodicity conditions on the fields that respect the coordinate identifications of the background, and we conclude that the state that we are describing, the kind of partition function that we are describing, is this one. We are in a thermal ensemble, so it's a mixed state. It's a statistical ensemble that has a finite temperature, finite angular velocity, and finite electric potential. So this is the conclusion of this wall analysis. And notice we have computed the Hawking temperature in a situation that is more complicated than what we could analyze via the direct method of studying the radiation. It's more complicated, but kappa is given, surface gravity is this one, and we have concluded that beta even now, even in this case, it comes from the analysis, is 2 pi over kappa. It's not 2 pi over 2 Rs, R Schwarzschild or R plus. It's 2 pi over kappa, really. This comes from the analysis. And this, again, you can repeat this in many other situations. But instead of doing that's another example, let's try to be much more ambitious now. So I'll start a new conceptual discussion, let's say. It builds on this, but it goes beyond this. So if there's any question about this before going on, just let me know. So this is the gravitational path integral. So let's see what we would really like to do. So the original motivation we had was to say, okay, we want to understand better black hole thermodynamics, see how it is interpreted, what does it mean, and we are doing that. But now ultimately we would like to somehow embed this in a theory of quantum gravity and deduce everything from quantum gravity, or vice versa, impose constraints on the theory of quantum gravity. So we now, at some point, we would like to consider gravity dynamical. So far, the gravity was like a spectator, and the QFT was defined in a curved diagram. But eventually, we want to make the metric and fluctuations dynamical, and the sum of those in the path integral. So we want to include this in the path integral. You may say, okay, but gravity is not renormalizable. What do we want to do? Okay, we would need to assume this is embedded in string theory, in a UV complete theory, and so the path integral that we are going to define should also contain all these other string theory degrees of freedom. This is correct, but before heading towards that, let's see where we get tomorrow. We'll try to use a bit of ADS-CFT to make this more rigorous, but this I leave for tomorrow. For today, let's assume we can define a gravitational path integral and try to deduce what we have seen so far as a semi-classical approximation of that path integral. So let's try to define the problem as if the metric was fluctuating. We are not going to solve the problem, but first we want to see how the classical picture that we have seen so far emerges. This also answers the questions why we have to impose, how does the classical picture is related to the quantum fluctuations. Everything comes from the full path integral and taking the semi-classical approximation where the metric is frozen. This is justified by the fact that at low energies, so the gravitational interactions is irrelevant because the coupling constant is dimensionful. So at low energies, it's irrelevant. So the other interactions remain, and the gravity can be treated classically. So that's what we are going to do. We take the semi-classical approximation in the path integral so that the gravity becomes classical and the rest is still the path integral. A priori, it can still be the path integral. So if we want really to be ambitious, in the gravitational path integral, we should fix the boundary conditions and allow the metric to fluctuate in the most possible general way. So in principle, we will need to sum over different topologies even, because different matrices can describe different space-times, and this is a complicated problem, of course, super complicated. This is a debatable question. So what I'm going to try to say now is that we want to consider semi-classical approximation, where the action that enters in the path integral is dominated by the solution of the classical equation of motion. There you don't want singularities. So at least for the classical saddle points, you usually exclude the singularities. Then in the fluctuating geometries, it's a bit, for instance, orbifold singularities are allowed usually, but okay, it's not something I would like to enter in. Let's try to be ambitious, but not too ambitious, one thing after the other. So we have this more complicated path integral, where now the matrix, we sum over polynomial matrix. Always the thing you should keep fixed in the path integral is the boundary conditions. Conditions for the fields, and in this case for the matrix, and everything else can fluctuate. We want to do this Euclidean. Now I motivate why. Well, some motivations are obvious. So ask me what's the measure for the matrix, etc. It's a bit formal, the thing so far. I want just to try to extract information from just consistency of the construction. So there is some measure for the matrix, for the fields. This is already Euclidean. So Euclidean path integral. So this, compared to the Lorentzian one, has better convergence properties, is slightly better defined mathematically, so better convergence, better defined, say, than the Lorentzian one. Euclidean versus Lorentzian, let's say. But there is a crucial motivation that, as far as I understand, what was really one of the main motivations that led Hawking and Gibbons to introduce all this. There is another motivation for considering Euclidean path integral instead of Lorentzian one in this gravitational case. Do you see what could it be, the motivation? Yeah, well, let's be a bit more specific. The convergence of the integral is basically what I already said here, that the Euclidean one is always better defined, even if I don't have gravity. But in particular, when I have gravity, okay, I don't know if this may, but a thing that is more related to what we saw so far is this story of the singularities. In the Lorentzian signature, I have singular space-time, black holes. We want to define, if we want to understand a bit better the physics of black holes, we want to understand what's the contribution of the black hole to the path integral. So we need to include this in the sum over geometries. But if it's singular, or if it is an horizon that we don't really know how to treat, it's almost hopeless, or at least we don't know how to define it. But if we go Euclidean, then the black hole is a regular geometry. It's just a regular geometry with some prescribed regularity conditions where the Lorentzian horizon was. And we can very well include it in just a sort of instanton solution or something like that. It's a regular solution to the Einstein equation with positive definite metric, and we include it in the sum without any problem. So we will see a bit later. We can study different contributions to the path integral. One comes from the black hole, the other one comes from flat space or some other solution. We compare, we see which dominates the path integral. All this is thermodynamics applied to black hole physics, and this comes from this definition with the path integral. So we need to know how to incorporate these geometries, and this is easy to do in the Euclidean case. So incorporate easily black hole geometries. And third motivation, okay, because the Euclidean path integral is what computes quantum field theory at finite temperature. So we can stay at finite temperature. So the boundary conditions that we specify is that asymptotically at large values of we introduce radial coordinate when we define the action, and we want that the matrix asymptotically is one of flat space locally, or if we have rotation, we want a matrix, say, of this type. If we have rotation and there is a gauge field, we impose these boundary conditions at infinity, like here, and we allow all possible geometries in the interior. So let's see how this is consistent with what we have seen until 5 minutes ago, before trying to make this jump. So what we have seen so far could be recovered from this more general situation by a semi-classical approximation, as I was saying. So we fix some geometry, and then we expand around it. And the geometries that we will fix are those that solve the classical equations of motion. But let's just see how it goes. So let's do saddle point. Suppose we have this, and we want to do some saddle point approximation. So we say that the metric, G mu nu, is some fixed background metric, G bar mu nu, plus the fluctuations. And same for any other field, including the gauge field. We are also integrating over possible gauge fields here. Any other field is incorporated in phi. And then we expand the action. I mean, this is really the most trivial thing, just basic semi-classical approximation. The only thing is that this contains also the metric. So we have the classical piece, the order 0 piece, plus some piece that is quadratic in the fluctuations. So it contains delta G, delta phi, and is quadratic in this. In principle, we have much more, but these are the leading contributions into the path integral. We can expect that the full partition function will be minus log z is I of G bar phi bar minus log of the integral over the fluctuations. So this path integral may be easy or hard to compute. Of course, I have all the corrections, but leading contributions are these ones. This one is the dominating one. These are the subleading, but leading with respect to other quantum corrections. And this may be easy or hard to compute. Maybe I'll say something tomorrow, let's see. But so far, let's focus on the classical contribution. So this should be the contribution from the solution that solves the classical equations, because it's what extremizes the action I. Right? The classical equations of motion extremize the action, so it's the dominating term in this sum, in this path integral. Is what minimizes or extremizes, say, the action. So I find the saddle point by extremizing the action with respect, so I impose the classical equations of motion. So this is the way we recover the solution. I was saying, okay, we want to impose regularity condition for a solution that solves the equations of motion. This is the reason, because it's the saddle point of the gravitational path integral. So here I have fixed the other fields too, but in some situations it makes sense to fix the metric, as we have done, and fix the background gauge field and allow some other dynamical field to fluctuate. Okay. So now we have our partition function, gravitational partition function, and we have established that it is computed by the action at leading order, and then we have contributions from quantum corrections. So let's try to compute this action. We have not computed it. We have defined it, but implicitly. If we compute it, then we can do thermodynamics, because we have the partition function. We can try to compute something from the partition function, like the entropy. We will see that from all this, entropy comes out and comes out right, independently of the way we have derived it so far. The entropy is some microcanonical partition function, right? It is the log of the number of states with assigned charges, assigned quantum numbers. This we are computing certainly is not microcanonical, it's canonical, say, if we do Schwarzschild, if we have angular momenta, it's grand canonical partition function. I spent all the time to discuss this. So it's what we have shown. So we will just need to pass from the canonical partition function to the microcanonical. That will be the entropy and will be the correct one. Okay, this is a bit ahead. So what I'm reviewing here, just for you to know, is the Gibbons-Hawking paper. It's one of the most famous papers from the 70s. This, from here on, say, it's a very short paper, it's 4 or 5 pages, it's nice to read. I'm just reviewing that. So there they gave a prescription. Not only, first they defined the gravitational path integral in Euclidean signature, and second, they gave a prescription for computing this action here. It's not complicated, but still it's the action of an infinite space-time. So we need to regularize the volume of the infinite space-time, or space in Euclidean signature, but still it's infinite. So we need to find a good way to do that. And yeah, maybe we can have the break now. The computation of the action takes some time, so we can take the break now, 10 minutes or so. And yeah. Okay, there are still quite many things we would like to discuss. So let's quickly see how the on-shell action is computed, the Euclidean on-shell action. Let's start from the simplest situation of the Schwarzschild black hole. So the action, the Euclidean action, let me see if I want to be Euclidean immediately. Okay, Euclidean action. Let me drop the E here. We are just Euclidean. We don't pass from Euclidean to Lorentzian in this lecture. So let's assume this is the Euclidean action. After I've done the analytic continuation, I have a minus sign, 1 over 16 pi, the integral of d for x square root of g r. And this is the, so since I want to describe Schwarzschild, I don't introduce the Maxwell term relevant for Kerr-Newman or Reisner-Nostrom so far. Then we will comment on what happens in that case. So we want to compute this action. So first guess, what could it be? In your opinion. Someone say 0, it's a natural guess, because the solution to the Einstein equations in the vacuum is Ricci tensor vanishes, so Ricci scalar also vanishes. So the contribution of some solution will have 0 here. And since it is 0, if it is 0, what thermodynamics are we doing? I mean, we don't have anything, it's 0. So one would say, okay, the classical contribution is 0, I have to go and check the quantum corrections, etc. But one can do better, because actually the space-time has an infinite volume. Right, this is infinite. If I don't have R, I integrate over an infinite space-time, I just get infinite. So we have infinite times 0. We need to regularize. When you have these situations, one always has to regularize something. And so you can say, okay, regularize the space. I suppose we integrate over R4, and we are Euclidean. R4, I take the radial direction. I fix my R to be at most R0. I regularize the space so that R, I introduce a cutoff in the radial distance, cutoff R0, cutoff, such that R is less or equal than R0. So I now integrate. I have my nice volume, it's finite. R is still 0, so 0 is the right answer. No, because now you need to add something here. Something is due to the fact that you want to have a good variational problem. You want to have a good variational problem for the metric here. In this case, we just have the metric. So, because what we want to compute is the extreme. We want to extremize the action, right? This is what we want to do to compute the contribution to the path integral. The saddle point is the extremum of the action. In order to compute the extremum of the action, we need to make sure that the variational problem is well defined. That is, the action is extremized on the solution of the equations of motion. But if you remember what happens when you compute the Einstein equations from here, you would definitely obtain r mu nu equals 0 in this case as equations of motion. But is the action based on that or not in general? Now we have a boundary. So I anticipate a bit. So if this is my manifold M, I will have some boundary term. Why? Because when you do the variation of the Ricci tensor, inside the Ricci scalar there is the Ricci tensor, so you obtain terms that have the variation of the metric, but also the derivative of the variation of the metric. And these are evaluated at the boundary. They are boundary term. This happens when you integrate by parts. And so far, I could say, okay, the boundary is at infinity, everything dies off. But now we've introduced a sharp boundary, a boundary at finite distance. And so we need to make sure that the variational problem is well defined in this space, so that when I fix the metric, I don't have also to fix the radial derivative of the metric. This is not a good variational problem. I cannot fix both things. So let me be more explicit. But I want to state a bit what's going to happen. This is not a good variational problem by itself when we have a boundary. We need to introduce some other thing here, a boundary term, that will cancel the wrong terms that come from here, so that the whole thing is a good variational problem with Dirichlet boundary conditions. That is, I keep the matrix fixed at the boundary, and I don't impose anything on the radial derivative of the metric. This is a good variational problem, and if I satisfy the equations of motion, the action will be extremized with these boundary conditions. That is what I want. But if I just have this is not enough. So this was first introduced by York, and then used by Gibbons and Hawking. That's why it's most usually called the Gibbons-Hawking term. I first write it down and then explain a bit more. So the correct sign should be this. So what is this square root of h times k? So we are choosing a boundary here by hand that is defined by r equal 0. So M is a hypersurface defined by r equal r0. On this hypersurface, we have a metric that is induced. The induced metric, so metric is Hij. Let me see, just to give you a taste of how to obtain that. If you have the full metric, ds2, it will be some n squared dr squared plus Hij dxi dxj. So this is the part of the metric that is relevant when I move along R, and this is red. This is the induced metric. Okay, so this is for hypersurfaces at fixed R. And K here is the trace of the extrinsic curvature of this induced matrix. So there is something like the extrinsic curvature. And then there is its trace. So its trace is just Hij, Kij. So here Ij go from, well, all the indices up to excluding R. So in our case, it would be 0 for the Euclidean time, 1, 2, and I'm not counting R here.
You're not going to add matter like a scalar field or something like that?
I'm not going to add matter fields here. I could do that. In principle, I should check that the variational problem is defined also for, but typically I would have that the scalar field is 0, and this would generically extremize the action, but in principle I have to make sure. For instance, if I introduce the gauge field that I was discussing before, if I want to describe Rasner-Nostrom, there is a gauge field, and you can see that there is no need of a boundary term. The variational problem for the gauge field is well defined without introducing extra boundary terms. If I keep the gauge field fixed, that's fine.
Yes, super. The last lecture we saw that it was within variation of the scalar field that was in this background.
Yes.
And now I don't have a scalar field, but I still interpret that I have variation. What's the particular?
the point, okay, yes, the point is that we will see we have finite temperature. So this means that whatever field I then introduce, you can also introduce any field that you will have to be consistent with the fact that the gravitational background is at finite temperature. So if you want to be at equilibrium, the field should also be at the same temperature. Yeah, I'm not describing other dynamical degrees of freedom. I want to contribute to check what's the contribution of the gravitational field. Because I assume that phi bar, the solution for the background, not the fluctuation, the solution for this is 0. Then I may have fluctuations of this, but these come later in the path integral. This is the contribution from the gravitation classical action. I didn't define what's the extrinsic curvature, so let me give it. Is a half of the Lie derivative along the normal vector. The normal vector here is basically the derivative along R. The normal vector to this hypersurface of Hij. It tells you how this hypersurface is bending in the wall space. The extrinsic curvature is not intrinsic, it's a curvature that appears once I embed this hypersurface in the full space. Just to be even more explicit, in our case, for matrix of this type, that are those that we consider, the expression for Kij does not involve this Lie derivative. I mean, it's the same as this, but it can be written in a simpler way. It's 1 over 2n. N is this component here of the matrix. The derivative along R of Hij. And this is evaluated in R equal R0. We will have to evaluate this on the hypersurface. Okay, this is K. So I'm not going to show that this is the right term, but let me just motivate what happens. So I have, when I vary the action, let me just vary the Einstein-Hilbert term. I obtain the equations of motion, as we know, times the variation of the matrix. Plus, I have these boundary terms that I was discussing before. So here it is. There is some x, some function of g and of the derivative of the matrix times delta g. These terms are fine because we can say we impose Dirichlet boundary conditions. We keep delta g fixed at the boundary. These terms go away. So the action is extremized after we impose the equations of motion. These are good terms for our Dirichlet boundary problem. But if you do the variation of the Ricci tensor, you obtain some other terms that contains derivative of delta g. Here I'm a bit schematic. I'm not putting the indices anywhere. I don't want to make this too explicit. But it's what you obtain. So I have derivative, space-time derivative, in particular the radial derivative of delta g. And I don't have a good variational problem if I impose both this and that. I should impose one, because I have second-order differential equations, so I should impose one boundary condition, and the other one is determined by the evolution dynamically, but not by imposing that the variation vanishes at the infinity. So I would like to remove this in the variation. So the solution of this issue is to introduce this term that precisely is such that the variation of square root of AHK is precisely such that it offsets this. Okay, so we are left, after we have done that, with an action that is correctly extremized upon imposing the equations of motion, Dirichlet boundary conditions. And now we come back to our problem, whether the action is 0, infinite, something in between. And now we have regularized our space. So this is something finite times something that is 0, so it will be 0. But there is... So the action, weird enough, is completely determined by this boundary term that we had to introduce to make the variational problem well defined. Okay, let me give some details. You can erase this. Of what you can do, all the computations can be done with the help of to be quicker with the help of some computer program. So we need to know what's the induced metric. We want to do this for Schwarzschild, right? We said Schwarzschild. The Euclidean section of Schwarzschild. Okay, this was the metric of the full space. We have identified the time circle. Notice also that it's important to have identified, to have periodic time, so that there is, when I integrate over time, I get beta, and this is not infinite. It's, I have compactified my time. Otherwise, even if I have a boundary term here, the boundary term is at fixed R0, but there is still an integral over time here, right? If time is quantified, this would give infinite. But now that would be proportional to beta a priori. So computing the trace of the extrinsic curvature, so you compute Kij. First you compute it, then you evaluate it in R equal R0. And 2 over R0 minus over 2R0 squared plus subleading terms. R0 is fixed but large, so we do an expansion in R0, R0 to the minus 4, and then there are subleading terms, obviously. And so I didn't give a name to this term, but since it's an important one, let me also write that name. Gibbons Hawking York boundary term. So this evaluates to, once you compute, do some computations, you get beta, again, because here is an integral over d3x. So maybe I forgot to write the integral d3x here. And then from integrating over the angular coordinates, theta and phi, I have coordinates r, radial coordinate time, Euclidean time gives beta. The integration over theta and phi will give some 4 pi. And, but here I have 1 over 8 pi, everything works out in such a way that in the end I have this. So even if the extrinsic curvature goes as 1 over R0, here I have to take the trace of that and multiply by the square root of h. In the end, I end up with something that contains R0. So we have been a bit too quick to conclude that this action is finite. Actually, now it seems infinite, because R0, when I remove the cutoff, I send the cutoff to infinity. Now it gives infinite. So first it was 0, then maybe it was finite, now it's infinite. We still have to be careful.
Sorry, but R0 is the cutoff and RS is the boundary of
RS is, we are doing Schwarzschild, so I have this metric. RS is a parameter in the metric, it's the Schwarzschild radius. I decide myself what it is. It was RS is 2m, but it's a parameter. So RS is finite, is something but finite. R0 is the cutoff that is larger than RS. So R0, by assumption, is larger than RS. I'm describing the part of the space that is outside the horizon and goes up to infinity. So R0 is very, very large, but I cannot remove it. I've regularized the space, but in the end, as in any regularization, I would like to get rid of the cutoff. And this seems to be an infinite action. But as usual, we have done regularization, but we should do the next step, which is renormalization, right? We should renormalize, remove the divergences. And this is an art. So sometimes it's intuitive, sometimes it's it's hard to understand which symmetries you're preserving. These whole issues of anomalies is related to this. Here, this is a classical computation. There is no issue with anomalies, but still, we need to be careful. We need to find a good prescription for removing the divergences. That is not just get rid of this, just forget this. That doesn't look like a good prescription. Yes?
Apparently, there is no physical equation that can lead me to introduce that boundary term.
No, the boundary term is definitely needed. Mathematically, is needed. It's not. Yes, in order to have a good variational problem. The physical intuition is that you want to extremize the action because you want to compute a saddle point. So you need to make sure that when you impose the equations of motion, the action is extremized. If you don't impose that boundary term, the action is not extremized when you have a boundary. So that is clearly needed, but it seems to lead to infinity unless I properly remove this divergence by doing something. So the idea here is that you want to compute, to understand what's the contribution of the black hole to the ensemble. So in principle, you would do a sum over all possible solutions and compare them. So when you compare the black hole, you would compare it to flat space. No? I have, say, in the sum, I have the action of the black hole, then I have the black hole, then I have the action of flat space here, say R4. In this prescription, the action of R4 is also infinite, because there is the same boundary term. And you want to compare the two. So the actual thing is to say, okay, I have an overall factor that is determined by somehow the vacuum, that is the action of R4. And then I compare, so this is 1 plus E minus the action of the black hole minus the action of flat space. And I want to understand what's this contribution to do the thermodynamics. This I consider trivial, and I factor out, and then I play with this. So the idea is to remove the action of flat space from my contribution. The action of flat space is also infinite, so I have a hope to cancel out this. But it's good to do this in a careful way. It's not just saying, okay, the action of flat space, I think this to be R0, and I forget R0. It's not going to work. So let me write what one does, because it's not immediate to get. So one prescription, renormalization prescription. So first I write it, so maybe it's more clear. Subtract the Gibbons-Hawking-York term from the one that we already have, computed for a boundary surface of identical intrinsic geometry, as the boundary that we have in our solution. So we want to keep the boundary fixed. In these different contributions, the boundary must be the same, because they must contribute to the same path integral with the same boundary conditions. So the boundary is fixed. And so whatever else we subtract, the boundary conditions must remain the same. So this is the reason of taking the identical intrinsic geometry as the boundary that we have in our solution, but embedded in flat space, so that it can be considered the correct Gibbons-Hawking term for flat space, for the vacuum state, say. But embedded in flat space. Now I'm going to write what this is. But is this clear enough? To subtract the Gibbons-Hawking-York term, same term that is here, but evaluated element for flat space. To keep the same boundary conditions as for the black hole. So the whole geometry must be the one of flat space, but the boundary must be the one of the black hole. I'm going to write what is the correct metric.
Sorry, but why do you think that contains the term of R4? So you're subtracting because you think you have...
I'm saying the flat space is a solution to the Einstein equations as much as the Schwarzschild solution. So it will, I want to compare the contribution to the path integral, to the thermal, so okay, I'm jumping to thermal language, but I want to compute the contribution to the partition function that is computed by the path integral, and compare the contributions of flat space and of this black hole, because I want to understand what's the contribution of the black hole compared to the vacuum. So I can compare solutions in this simple way. In principle, this comes from this is in Z, no? The classical contribution of Z is the sum of saddle points, and I have to take the one that dominates. Yes?
I understand that this description is reasonable, but is there any sort of analog to how QFT there is scheme independence of zero quantities? So for example, if I choose another boundary for M which is not a sphere, or then subtract something else which is not flat space, to physical quantities such as the entropy change?
Yeah, okay, so the question is interesting, and it may lead also to confusions, or maybe something is not well defined. So indeed, renormalization also is always delicate, because the scheme you introduce may preserve or not the symmetries that you want to preserve or break, or say that you want to preserve. So if the regularization that you introduce is fine, preserves all the symmetries, and so on, it could still have ambiguities when I send the cutoff to infinity. This is a possibility. Here I don't immediately see what the ambiguity could be, but okay, we could discuss. I know better the situation in ADS space, where everything is similar. I mean, basically you play the same game, you have the same issue that the boundary term gives you infinity, and there I know how to classify the possible ambiguities by introducing local counter terms that are finite. So in principle, I would introduce, for instance, a term that is, well, here the boundary is three-dimensional, I don't even have a finite term to introduce. In general, here I don't see what could be the ambiguity. I can discuss a bit more that when we come to ADS space, maybe. Maybe it clarifies. Yes? Yeah.
Make sure I understand the renormalization of the description. So
I haven't finished the discussion, but yes. No,
it's equivalent to saying that you embed the surface isometrical in that space and compute it on your...
Yes. Let me write the metric for this, the full metric of flat space that I want to consider for solving this problem. The metric of flat space, so it's not the metric of Schwarzschild, the metric of flat space is dr squared plus the induced metric that I want to use for computing the Gibbon-Soking term that I want to subtract, hij flat dxi dxj is dr squared. Now I write is 1 minus rs over r0 d tau squared plus r squared d omega 2. So let's look at this. R squared omega 2 here. This part is r squared d omega 2, but it's not important. What is important is this part. Because you see, this is the part that is fine for describing flat space, but it's the same that we have here. What is different is this is the radial coordinate r, so this component is r-dependent. So this is not, if you compute the curvature, it's not the flat space. But here I have fixed r equal r0. This is r0, not r. It's fixed. So this is just a rescaling, fixed, constant rescaling of the time coordinate, right? The rest is the metric of flat space. So I'm just measuring time with this rescaling factor here, but it's the metric of flat space because I fixed R0. Is this clear? There is no dependence on R except then here, R squared, the omega 2. But this is certainly, I can reabsorb this constant factor into tau. And then it's the metric of Minkowski. But I want to have it there because then I want to say tau is identified up to beta. And when I evaluate this at R0 and this at R0, then they coincide. So the metric induced on the boundary at R equal R0 are the same. So of identical intrinsic geometry on the boundary as del n, but embedded in flat space. This is what I've done here. This is flat space, this is the induced matrix, and this is definitely the induced matrix, the same induced matrix as the one of the black hole when I take R equal R0. Is it clear? If you have questions, let me know. You need to think a little bit about that, but after all, it's not so strange. It's precisely what you were saying. I take the same induced matrix for R equal R0, and now I embed it in flat space instead than in the black hole geometry. Now we should call the Gibbon-Hawking term for this. Let me write it here. 1 over 8 pi integral of square root of h flat k flat. Is beta because, as I say, that the intrinsic geometry of the boundary must be the same. I also have to declare that tau is identified up to beta. So when I integrate now over the tau current, I still get beta. So I get beta, R0, good, minus Rs over 2. And then I have other terms that go away when I send the cutoff to infinity. Like, also here I would have other terms that die off when I send plus O of 1 over R0 or something like that are completely irrelevant. So now we have obtained the leading order, the divergence is the same as here. The opposite sign is that because here I'm already computing 1 over 8 pi, I'm already subtracting this from this. And here a plus. I'm going to write the final answer in a second, but so you see the divergence will cancel, but it's not the same as having forgotten the divergence here because I get a finite term here, 2. The point is that, let me first write the final answer. So the final answer is the renormalized action that is, just to be even more explicit, 1 minus 1 over 16 pi, the integral over m d for x square root of g r, which does not give any contribution, but it's there. Then we have the Gibbon-Hawking term. And then we subtract the Gibbon-Hawking term for flat space that we have just computed. H flat, K flat, with the prescription up there. So this is 0. The divergence is, well, let's also write plus beta minus R0 plus 3/4 Rs plus beta R0 minus Rs over 2. So divergences go away, and I'm left with a finite term that should be 1/4 beta Rs, which, if we recall that for Schwarzschild, beta is 4 pi Rs. This we have computed by imposing regularity of the Euclidean solution. We have computed it before. In the end, we are left with pi Rs squared. Okay, so we have computed the renormalized action for the Schwarzschild black hole by subtracting this contribution of flat space. And we would like to test now if the partition function that is computed by this is meaningful. Yeah, that's a good question. I thought a little bit about that. The answer should be no, but I'm not completely sure. So whether this spoils your variational problem. Yeah, I think the final answer is not, but I also got confused by that. The only proper answer can be no, it should not spoil the variational. Yeah, that's right. That's right. The point is that this helps because here I have R0 and R0 is fixed. I don't have any radial derivative, so it does not contain anything non-trivial along the radial direction. It certainly, when I vary that, it does not contain delta of derivative along R of Hij, because Hij does not depend on R, depends on R0. I guess this is also, at least for the relevant part. There is this part, but it's not important here.
Yeah, but then we have to change this converter for every metric we are considering, right?
Yeah, this is there. Now it's our prescription. Whatever solution we consider, this must be there now. We have decided this is the counter term that regularizes the action. For any other evaluation we may want to do for any other action, this is the prescription for subtracting the divergence. With that, we cannot change. This is part of the definition of the theory, if you want, the way I renormalize. So once this is prescribed, for any other solution with the same boundary conditions, it must be there.
So then that depends on the metric we are considering in order to...
It depends on the boundary metric, not on because it's the boundary metric embedded in flat space. So it depends on the boundary metric. That this is something we want to keep fixed in whatever solution we consider. It again comes back to fixing the boundary conditions. So let's see if this result we obtain for our partition function is meaningful. So expressed in this way, so it was minus log of z. This is a function of beta because we want to interpret this in the canonical ensemble. So here it's expressed in terms of Rs, but Rs and beta are related in this way. So I can also see this as a function of beta, of course. Let me just write. It is just what is there expressed as a function of beta instead of Rs. So here is our partition function, canonical partition function. Now we do thermodynamics. We know we can interpret this as a system at finite temperature. We know what we apply what we know from thermodynamics. That is that the energy is minus the derivative with respect to beta, the inverse temperature, of the logarithm of the partition function. This is just thermodynamics, is the definition of energy in the canonical ensemble. Is beta over 8 pi. And if you remember what is beta, is 4 pi Rs. So it's 4 pi Rs divided by is Rs over 2, which is m, is the Schwarzschild mass. Okay, it's encouraging. We obtained the energy is the mass. Good. Then we can do something slightly less trivial, compute the entropy. The entropy is log of z of beta plus beta times E. What I'm doing here, I'm rearranging the terms, but it's like doing the Lejeune transformation of the canonical partition function with respect to the conjugate variable, that is the energy. So you should see this as Z canonical. This is log, the entropy is log of the number of microstates, that is the microcanonical partition function, that is a function of the energy. This is the entropy. So the two are related by Legendre transformation. This is the expression for the Legendre transformation, and this complements the Legendre transformation. E is the derivative log of Z. This comes from extremizing this expression with respect to beta, right? If I extremize this with respect to beta, I obtain precisely the definition of energy. This comes from extremizing this with respect to beta. S does not depend on beta. If I extremize everything with respect to beta, I get this. Okay, let's do the computation. We get beta squared over 16 pi from the first term. No, this is already the result. Yeah, in this case, it's a bit, seems trivial because it's again this. It's work out kind of trivially in this case, but when you generalize this, it's nicer. Anyway, you get pi rs squared. It's a over 4. Remember, the area was the area of the two spheres of radius rs, so it's 4 pi rs squared. So pi over rs squared is the area over 4. So we have deduced the entropy from thermodynamical considerations after computing the canonical partition function by this Euclidean technique. After we have the partition function, we can manipulate it as a thermodynamical object. So we define the energy, we define the entropy by using standard basic thermodynamics, and everything works out. So we have computed the area, the area law for the entropy. We have established the relation between area and entropy in a completely independent way from what we have done in the other lectures. Again, there is consistency with thermodynamics, but the way the thermodynamical partition function is derived is different from what we have seen. And again, we see that this is coming out consistently. And if you repeat this in many other cases, it's always the same, a over 4 that you get. In the remaining 5 minutes or so, I would like to quickly discuss the case of the rotating black hole, because we have done all what was needed to get there. So let's do this in the remaining 5 minutes. So the Hongshell action now in the grand canonical ensemble. So no more for the Schwarzschild black hole, but for Kerr-Newman, so that we have angular momentum and electric charge. So I'll be more sketchy here. The procedure is very similar. Again, I first start from the action. So this is the action that is relevant for Schwarzschild, but for the Maxwell field, I need the Maxwell field now as well. F mu nu, F mu nu. So I have the Maxwell field, and here I use the same prescription that was there for the regularization. So I have 1 over 8 pi integral of d3x square root of h flat k flat. Sorry, it's not very visible, but is what I wrote here. I use the same prescription for regularizing the space-time. Is it clear what I'm doing? I don't want to rewrite the action. I just added a Maxwell term and used the same prescription as before, because the variational problem for the Maxwell field is already fine. There is no need to introduce extra boundary terms for that. And so there is no need to introduce extra boundary terms, but now F mu nu, this Maxwell term will contribute, can give a finite term. So one way to compute it, I'm not going to do all the steps, but is is, so we have to compute a term like this. So this is easily seen in differential form notations. Is f wedge star f with a factor of 2. Then you can use integration by parts, or if you want Stokes, to write it as d of a wedge star f minus a wedge star d star f, and then this vanishes because of the Maxwell equation. This star f equals 0 is the Maxwell equation, and this is a boundary term that just gives the integral of a wedge star f. This you need to evaluate at the boundary that is at r equal r0. Del m, remember, is the hypersurface r equal r0, and r0 is my cutoff. So you need to do all this. Suppose you have done that, you subtract the same terms that we have seen here.
Actually, the boundary actually the
Yes?
to the horizon or to the hypersurface limiting the
Yeah, very good. In principle, you have the contribution both from infinity and from the horizon. Indeed, I've neglected something. In principle, you should consider the full boundary. It is contribution from the horizon and the contribution from, if there is a boundary. If there is a boundary of, if this does not die off, the contribution from infinity, from the horizon, the x, or it is no more the horizon, where the space ends. There is a contribution from this and the contribution from r equal rs, r plus here. Kerr-Newman has this. Consider this as well. But once we have imposed regularity of the gauge field and of the metric, this contribution is 0, because the gauge field will go to 0. At least the part along T, I think the rest as well. Anyway, in principle, you have to do this, but you also have to make sure that the solution is regular before computing the integral.
Once we have a regular solution, why that one should be a boundary? Isn't it part of the interior of the network?
Yeah, I agree. I agree as well. I agree with this. If you are sure that you have done everything properly, and you have a smooth geometry, smooth solution, this will not. You may even try to do that. I mean, assume this is the other extreme of integration. You will see that there is no contribution. That is correct. But suppose you have done things not so properly, and there is something left there, like a component of the gauge field that should not be there. You would get something from there, in principle, and you have to check if it makes sense or not. But indeed, here discussing the contribution of the gauge field from the matrix, yeah, get anything clear. Okay, so let me just give you the result after all the dust has settled down. So the result for the renormalized action of the Kerr-Newman solution is beta over 2 m minus phi q. So m, remember, q are parameters of the solution. And here I'm taking, as always, p equals 0. J is not 0. The angular momentum is non-zero, but it doesn't enter in this expression. So this is what you get. So again, we should consider ourselves in the grand canonical ensemble. We have considered, so this is minus. We have considered the action. We have computed it. We are interpreting this as the contribution to the grand canonical partition function that depends on beta, omega, and phi, the same variables we had before. And now we want to do some thermodynamics. Okay, let's see what's a good way to do that. Let's use the SMAR relation. Well, first, let me do it in another way. One can verify something. It's not immediate to do that, but one can do this. One can show that j, although it does not appear here. It's 1 over beta del log of z with respect to omega when I keep beta and phi finite. Then I can show that q is 1 over beta del log of z over del phi when I keep beta and omega fixed. M is minus del log z over del beta, omega and phi fixed, plus omega j plus phi times q. These are, so let me first comment on these expressions. These are the expressions for the angular momentum, the charge, and the mass that you would obtain when you do the grand canonical, when you work with the grand canonical ensemble. You have the grand canonical partition function, and these are the definitions of the different charges. In the notes, I have added a small appendix with the very basic statistical mechanical things, and these are explained, or these formulae also are shown there, so that you may get convinced by this. So this is standard thermodynamics in the grand canonical ensemble. And you can check that if you do these variations of this expression here, indeed you get J, Q, and M. It's not so obvious. J was A times M in the Kerr-Newman solution. It's that. It's not so obvious because this renormalized action is not expressed in terms of the independent variables that are beta, omega, and phi. Here I have M, here I have Q, so I should invert this and express Q as Q of beta, omega, phi, and same for M before doing that. Or I've written a footnote in the notes explaining how to make this comparison. I mean, you just use the chain rule, you vary with respect to the parameters, and you check that it is correct. Anyway, let me just conclude. This, you can think a little bit more about that. So let's see what can we do after having checked the relations, the charges are correct. So we can recall the SMAR relation, generalized SMAR relation. It was saying, we saw that long ago, that the area over 4 is beta. We saw the SMAR relation with kappa. There was kappa here. Now we have understood that kappa and beta are related, so now I write it in terms of beta. And there was 1/2 of M minus omega j minus 1/2. I also introduced this contribution that we didn't really prove, but it was left as an exercise, the contribution from the charge. So this is the SMAR relation. So using the result we have up there for the renormalized action, this is the same as log of z plus beta. You see, I is minus log of z, and it is that expression up there. So here I have similar terms, m phi times q. So I just rearrange things, is beta m minus omega j minus phi times q. Is this something you agree with? Any complaint? Anything not clear? Well, if we all agree, we have concluded. Just let me see. Here we are again defining Lejeune transformations. A Lejeune transformation. Here we have a function of beta, omega, and j. Then these relations up here are telling us that j is conjugate to omega, q is conjugate to phi, m is conjugate to beta. And so when we do the Lejeune transform, what we obtain is the partition function in the ensemble where beta, omega, and j, and phi here, are replaced as independent variables by the conjugate charges. So this is log of Z microcanonical that depends on E, J, and Q. And this, by definition, is the entropy. So we have proved by this Euclidean method that area over 4 is the entropy also for the Kerr-Newman solution. And this, again, can be generalized in many ways. Okay, just to see what we are going to do tomorrow, we will quickly see ADS black holes and thermodynamics of black holes in ADS. I would just to do similar things in ADS and compare the action of ADS and the action of the black hole in ADS. And then we will do something even more ambitious, that is defining the quantum entropy, the quantum version of this entropy for extremal black holes using the formalism of Ashok Sen and collaborators. Okay, this is for tomorrow.